This is part 1 of the Chapter 9 review. So let's begin with problem 1 of the review. Find the value of x, then tell whether the side lengths form a Pythagorean triple. So first, we're going to apply the Pythagorean theorem, which says that the sum of the squares of the legs of a right triangle equals the square of the hypotenuse. So let's begin. And for number 1, we'll say 6 squared plus 10 squared equals x squared. We're going to take the square root of both sides, and square root of x squared is just x, and this value comes out to 11.7 approximately. Let's make that approximate. Clearly this is not an integer, therefore this is not a Pythagorean triple. 6, 10, and 11.7 is not a Pythagorean triple. Pythagorean triple is a set of 3 integers that satisfies the Pythagorean theorem. And you can plug it into an equation that satisfies the Pythagorean theorem, most commonly referred to as a squared plus b squared equals c squared. This is not the Pythagorean theorem. It's simply an equation that represents the Pythagorean theorem, where a and b are legs and c is the hypotenuse. Alright, let's try number 2. Before we go any further, I'd just like to recap what a Pythagorean triple actually is. A Pythagorean triple is a set of 3 integers that satisfies this expression. And so the 3 most common ones that you're going to find is 3, 4, 5, 5, 12, 13, and 8, 15, 17. If you remember from our lessons, these aren't the only 3. There's virtually an infinite number of them, but multiples of any Pythagorean triple are also Pythagorean triples. So we could take this, multiply it by 2, and it would also be a Pythagorean triple. 6, 8, 10. Likewise with any of these others, we could multiply each one of the pieces by a common factor, and that too would be a Pythagorean triple. So one of the tricks is to take a look at your sides and see if the 2 that they give you, it has a common factor. In this case, there's a common factor of 4. And 16 divided by 4 is 4. 20 divided by 4 is 5. So that looks like it's going to be a 3, 4, 5 Pythagorean triple, which would mean this side would be 3 times 4. Let's see if we're correct. 16 squared plus x squared equals 20 squared, because 20 is the hypotenuse. Subtract 16 squared, x squared equals 20 squared minus 16 squared. Take the square root of both sides, x equals the square root of 20 squared minus 16 squared. When we put this in our calculator, this does in fact equal 12. So we were correct that this was 3 times 4, 4 times 4, 5 times 4. This is a 3, 4, 5 Pythagorean triple. Now let's move on to 3 here. And we have 7, 13, and x. Doesn't look like one of the standard ones. Let's just go ahead and solve it. We have x squared plus 7 squared equals 13 squared. X squared equals 13 squared minus 7 squared. And x equals the square root of 13 squared minus 7 squared. Put that in our calculator, and x comes out to about 10.6. So this is not a Pythagorean triple. So let's move on to the next problem. In these problems, we're asked to verify that the segment lengths form a triangle, first of all, and then we need to determine if the triangle is acute, right, or obtuse. Now there's 2 parts to this. The first one is the triangle inequality theorem, which tells us that the sum of the measures of any two lengths of the sides of a triangle must be greater than the third. The second part of this question involves the Pythagorean inequalities, and those are what tell us whether or not the triangle is acute, right, or obtuse based on the relationship between the side lengths. So let's summarize these right here. Just for reference purposes, I'm going to call our largest side length C and the two smaller ones A and B. So what we want to do is put the longest side on the left and the two smaller ones on the right. And what I'm going to do is I'm going to take the sum of the squares of the two small ones on this side and the square of the biggest one on that side. And I'm going to do this 3 times. And what we want to do is we want to discover if the square of the longest side is less than the sum of the squares of the other two sides, then we're going to have an acute triangle. If they're equal, that satisfies the Pythagorean theorem, so this is a right triangle. And if this one's greater, then it's obtuse. And the reason for that is if you have a right triangle with a right angle, the square of this side must be equal to the sum of the squares of these. If this side is less than, then that means that we're going to have a situation where it's doing this. And clearly you can see that angle is smaller than the right angle. So this side got shorter, therefore this is going to be an acute triangle. And the opposite is also true, that if the longest side is greater, then this angle is going to be bigger than a right angle, making the triangle obtuse. So that's the general idea behind the Pythagorean inequalities. So let's go ahead and work problem 4. We can see that 6 plus 8 is 14. It is greater than 9. So yes, this is a triangle. And to see if it's acute, we solve this expression. Take the longest side and square it. We take the two smaller sides and square them, add them together. And what comes out will be whatever sign goes in here will tell us whether it's acute, right, or obtuse. So 9 squared is 81, 6 squared is 36, and 8 squared is 64. 64 plus 36 is 100. Clearly, this is greater than this, so that's less than. The triangle must be acute. All right, let's do the same thing for problem 5. This one's not quite so easy because we don't really know right off the top of our heads whether this is longer than this or this is longer than this. It would appear that this is the longest side, but let's just check in our calculator. So I've just written down that this one is approximately 2.8 and this side is 10.4. So it looks like this is in fact the longest side. So we have 6 square roots of 3 squared and 10 squared plus 2 square roots of 2 squared. Now let's go ahead and work this through. The square root of 3 squared is just 3, and 6 squared is 36, so that's 36 times 3, that's 100, and the square root of 2 squared is 2, and 4 times 2 is 8. So let's see what 36 times 3 is. That comes out to 108, and we have a 108 here, and so this is a right triangle. These are equal, so this is right. And clearly it is a triangle, or else this wouldn't have worked out. So, let's move on to number 6. Here, it would appear that this is the longest side, but let's calculate it just to be sure. And this side does come out to about 22.4. So this is the longest side. So we have 3 square roots of 55 squared and 13 squared and 18 squared. Now let's work these out. This comes out to 495. 13 squared is 169, and 18 squared is 324. These two add together to 493. So 495 is greater than 493, so this is an obtuse triangle. And all 3 of these are in fact triangles. Alright, let's move on to the next problem. In these problems, it appears we have some special right triangles. Here, this is an isosceles right triangle, which makes it a 45-45-90. Here is a 30-60-90 and another 30-60-90. So let's work on problem 7. And we know that the relationship between the sides of a 45-45-90 is a square roots of 2. So to solve for number 7, we know that x is 6 square roots of 2. And even though it's possible to approximate this to 8.5, the proper answer is 6 square roots of 2. Whenever possible, you should always give your answers an exact value as opposed to an approximation, unless an approximation is called for by whatever question you're answering. Alright, let's go ahead and work problem 8. Problem 8 is a 30-60-90 right triangle, and so we know that the relationship here is the side opposite 30-degree angle is A. So let's just write that in here. The hypotenuse is 2A, and that's all we have to do now is to determine what the value of A is. So if 14 equals 2A, divide by 2, 7 equals A. And since we know x equals A, x equals 7. So let's move on to problem 9. Here we have a 60-degree angle. This is the 30-degree angle. So we know the side opposite the 30-degree angle is A. The hypotenuse is 2A. Since A equals 8 square roots of 3, 2A is 16 square roots of 3, and x equals 2A, so x equals 16 square roots of 3. Alright, let's move on to the next problem.